So Professor Bernard Bercu is ready with his second talk to deliver today. Please welcome Professor Bernard Bercu.
Thank you.
Thank you.
So,
Over to you, Bernard.
okay. So, can you hear me well?
Yes, sir.
Okay, good. So, we were talking about Hovding's inequality given here. And we have seen the beginning of the proof of the inequality. And we prove this lemma. If you have a random variable with zero mean, which is bounding by below and above by A and B, you can compute the Laplace transform of this random variable, and the Laplace transform is smaller than exponential t squared over 8 times b minus a squared. And we saw the proof yesterday. Okay, so now we are in position to prove the Hovding inequality. So I take two numbers, two positive numbers, x and t, and I look at the probability that Sn minus its mean is greater than x. So we saw yesterday that if we multiply here by t, we will not change the sign of the inequality. Before t was negative, now t is positive. So the probability that Sn minus its mean is greater than x is the probability that t times Sn minus its mean is greater than t times x. So it is also the probability that exponential t Sn minus its mean is greater than exponential t. And if we go back to Markov inequality, okay, if we go back to Markov inequality, just a moment. So I go back to Markov inequality, and I can use it now because the random variable is positive, because this is exponential t Sn minus its mean is positive. So this is smaller using Markov inequality than exponential minus tx times the Laplace transform of Sn minus its mean. So if I write yk to be xk minus the mean of xk, the Laplace transform of Sn minus its mean is the Laplace transform of the sum of yk. So now I have to compute the Laplace transform of Sn of the sum of yk. Okay. Yn is a sequence of independent random variable, and yk is between ck and dk almost surely, because xk is between ak and bk. So yk is between ak minus the mean of xk and bk minus the mean of xk. And the important point here is that dk minus ck, if you compute it, it's exactly bk minus ak. So I can use the previous lemma, and using the previous lemma, I can't obtain a good upper bound for the Laplace transform of the sum of yk. The Laplace transform of the sum, as the random variables are independent, it is the product of the Laplace transform of x of each random variables yk. And by the lemma, by the previous lemma, the Laplace transform of yk is bounded by t to the power 2 divided by 8 times bk minus ek squared. So the product here is bounded by exponential t squared over 8 times the sum of bk minus x squared minus ak squared. So if I go back to the calculation, here you have exponential minus tx, and so you have exponential minus tx here, and you have to add t squared over 8 dn, where dn is the sum from 1 to n of bk minus ak squared. So now we just have to make an optimization over all positive values of t. So if I denote phi t, the function tx minus t squared over 8 dn, so I can compute the derivative, and I obtain that this function is maximum for which value of t? It's a question, so you compute the derivative as before. The second derivative, you can see that the function phi t is a concave function. So it is maximum where the first derivative is 0, and the first derivative is 0 if and only if t is 4x divided by dn. So if I plug this optimal value here, I obtain that the probability that Sn minus its mean is greater than x is smaller than exponential minus 2x squared divided by dn. Okay. Finally, here in the Hofding inequality, you have an absolute value here. You have an absolute value and you have a 2. So using the same calculation as before, that is replacing xk by minus xk, we obtain the same result. We obtain exactly the same result, the same upper bound. This is why if I put an absolute value, I will obtain 2 times exponential minus 2x squared divided by dn. So the Hofding inequality is proved. 2 times exponential minus 2x squared divided by dn. So the proof is simple, and it only relies on the convexity of the exponential function. Do you have questions about the proof? Do you have any questions? No questions? Sure? Okay. So you hear me well? No questions, sure? Udita, you have questions or no?
No, sir, I understand it.
Okay. So now we will improve the Hovding inequality. So if you people making research, every day you can look at archive. I think you know the website archive. And in probability and in statistics, you have many papers every day. And recently, you you can see I've seen two papers dealing with improvement of the inequality. So many people are trying to improve the Hovding inequality. It's not, it's difficult to improve it. We will see a simple improvement of this inequality. Okay. So now it's a work, I've made this work with Bernard de Lyon and Emmanuel Rio. It's in my book. And you will see a first improvement of the inequality. So the idea is as follows. Imagine you have a random variable x with zero mean, which is bounded by a and b. We have computed the Laplace transform of this random variable, and we have shown that the Laplace transform is smaller than t squared over 8, the exponential of t squared over 8 times b minus a squared. So the Laplace transform is bounded by this quantity. It is exactly the lemma here. Okay. And our idea is to improve this lemma. So if you look at the proof of the lemma, you can see that the Laplace transform of my random variable is smaller than 1 minus p exponential minus p st plus p exponential 1 minus p. So our goal now is to find a better upper bound for the left-hand side. Okay. And a lemma is as follows. The left-hand side is smaller than phi p times t squared divided by 4, where phi p is the function given here. And this lemma can be found in the Hovding paper. It's not our contribution. This lemma was established by Hovding a long time ago. And people are rediscovering this lemma, but this lemma, so you can see on paper, this before it was exponential t squared divided by 8. Now it's phi p times t squared divided by 4. So the function is here. And we will see a draw. And I will better explain the draw. The red curve here, is the left-hand side here. The red curve is the left-hand side for a fixed value of t, for example, for t equal 1, and for p varying from 0 to 1. So this is a fixed t. Let's take t to be 1. So I make a draw of p exponential 1 minus p plus 1 minus p exponential minus p. So the red curve is here for p varying from 0 to 1. Okay. The blue curve is the one given by this lemma. So I fix t and I make a draw of my function phi p. Okay. So this is the blue curve. Okay. And the black curve is given by how can I the black curve is given by the upper bound of phi. The black curve is given by 1 plus 2p1 minus p divided by 3, and p is varying from 0 to 1. So as close as we are to the red curve, as better as we are. If we are very close to the red curve, you will improve Hofding inequality. Okay, and we can observe that the first lemmas we saw yesterday, the upper bound is exponential t squared divided by 8. So if t is fixed, the difference is simply between 1 over 8 and 1 over 4. So it's a half, and a half is really not a good upper bound, because the red curve is the maximum of the red curve is here. So if you are a good mathematician, and if you can improve this lemma by another function, psi of p, you will improve Hofding inequality, and you will write a very an excellent paper. So just think to this lemma. If you can improve it, you will really obtain a very good result and a very good paper. Okay, so everyone is okay? So my first question is, can you improve this lemma? And if you can improve this lemma, you will have done a very good job. Okay. So a second keystone lemma. The first lemma is this one. A second keystone lemma is given by this lemma. Imagine you have a random variable with 0 mean, smaller than 1. I assume that the random variable is smaller than 1. Then you can find an upper bound of the Laplace transform of this random variable by exponential psi of v t squared divided by 4. Okay, and this lemma is more or less the same as this lemma. Okay. Okay. So thanks to those two lemmas, we improve of the inequality. Before, the probability that the absolute value of Sn minus its mean greater than x was smaller than 2 exponential minus 2 exponential minus 2 x squared divided by dn. Now, in the denominator, you can see the variance of. So, if you obtain an upper bound variance term, it will be better than many other results. For example, you can observe that dn is always greater than 4 times the variance of Sn. So, this ratio here is always smaller than the ratio given by Hofding inequality. Okay? You can see it well?
Yes, sir.
Okay, good. So thanks to this result, we slightly improve Hofding inequality. So the proof is as follows. The proof is more or less the same as the proof of Hofding inequality. So the probability that Sn minus its mean is greater than x is smaller than exponential minus tx squared times the Laplace transform of the sum of yk. As before, the yk are between ck and dk, so as before. So using the previous lemma, we can find an upper bound of the Laplace transform of yk, which is slightly different than the one we saw before. And we already saw that my function phi here, my function phi is always smaller than 1 plus 4v plus v squared divided by 3. So I can use it. 1 plus 4v plus v squared divided by 3. And I will, v will be vk, which is a variance of yk. So if I use this, what will I have obtained? T squared, the t squared here. 4 times 3, it's 12. So the 12 here. The sum of dk squared, the dk squared is here. And as phi is smaller than 1 plus 4v plus v squared divided by 3, I replace this 1 plus 4 vk dk squared plus vk squared vk over dk squared at the power 2. So vk squared over dk at the power 4. Okay. And now I continue the calculation. So easy calculation. I will not go into details, but Vk is smaller than Ck dk, and dk minus Ck is bk minus ak. So you plug these two quantities here, and you will obtain dk minus Ck squared, which is bk minus ak squared, and you will obtain 2 Vk here. And the sum of Vk is my variance term. This is important. So the sum of Vk is my variance term. And here you have the sum of Bk minus Ek squared, which is my dn term. So you obtain this. And now the rest of the proof is to find an optimal value of t. And this is exactly as before. I denote phi t to be t times x minus t squared over 12 dn minus 2 vn. So the function phi, I can compute the first and the second derivative. The second derivative is always positive, so my function phi is a convex function. A concave function, no, is always negative. Sorry, is always negative. So yes, is always negative because my function phi is t times x minus t squared over 12 dn minus 2 vn. So the first derivative is x minus t over 6 dn plus 2 vn. The second derivative is minus 1 over 6 dn plus 2 vn. So this is negative. So my function is concave. And to find the value maximizing my function phi, I have just to compute where the first derivative is 0. And the first derivative is 0 if and only if t is 6 times x divided by dn plus 2 vn. So I plug the optimal value in the first line here, and I obtain minus 3x squared divided by dn plus 2 vn. So by the same token, replacing xk by minus xk, you obtain exactly the same result. So the absolute value of the probability that Sn minus its mean is greater than x is smaller than 2 times exponential minus 3x squared divided by dn plus 2 vn. So we got the proof here. Okay. So this result is only interesting if Vn is very small comparing to Dn. If Vn is, the more Vn is small, the better will be this inequality, because imagine that yes, the more Vn will be small, the more 1 over dn plus 2Vn will be large. So exponential minus, because of the minus term, exponential minus 1 over dn plus 2Vn will be small. The small Vn is the if Vn is very small, dn plus 2Vn will be very large, and so minus exponential minus will be small. So I repeat myself. This result is interesting only in the situation where Vn is small comparing to dn. Okay. Do you have questions?
Sir, how the improvement of Weberding's inequality or any other inequality goes? Like B. De Leon Rio in 2015 work on the Weberding inequality and give a better approximation. Then based on that B. Dallin Rio's theorem, the people work on the to and get a better inequality.
You are if the closer, for example, the probability that Sn minus its mean greater than x, thanks to Hofding inequality, we saw that this probability is smaller than 2 exponential minus 2x squared divided by dn. Okay. So if you find an upper bound which is smaller than this upper bound, you will improve the Hofding inequality. So we obtain this bond, which is smaller than the bond given by Hofding inequality. So it is an improvement. Okay?
Okay.
So if you are able to erase dn, and in the denominator, if you are able to obtain, for example, 2Vn, if you are able to obtain, for example, that the probability is smaller than 2 times exponential x squared divided by 2Vn, you will obtain the best result you can never obtain. So okay.
Okay, sir.
Okay. So now we will switch to Kramer-Chernoff calculation. You know the Kramer-Rao inequality. Kramer-Rao inequality in statistics.
Yes, sir.
So
Yes, sir.
you know Rao, of course, and Kramer has done they established the Kramer-Rao inequality. Now it is the same Kramer, the Kramer-Chernoff calculation. Okay. So the proof of many results, the proof of Hofding inequality was relies on the convexity of the exponential function. Now we will see the proof of Hofding theorem, and it will rely on the concavity of the logarithm function. So imagine you have x1, xn, a finite sequence of independent random variables. They are not necessarily sharing the same distribution. This is important. Not the same distribution. They are only independent. And I look at the sum. Then the Laplace transform of exponential, the Laplace transform of Sn will be always smaller than exponential nLt. The Laplace transform of Sn will be always smaller than exponential nLt. So 1 over n, the log of the Laplace transform will be always smaller than Lt. And Lt is given here. So in the very special case where the random variable, they share the same distribution, Lt is the log of the Laplace transform of the same distribution of x1, xn. But this result is interesting when they are not sharing the same distribution. Okay, so another draw. Illustrating the concavity of the logarithm function. Imagine you have two positive values, a and b. A here is 2 and b is 8. In blue, you have the log function, the logarithmic function. So here you have log a, and here you have log b. So in blue, the logarithmic function. And in black, the line between the 2 points, a log a, b log b. So this line, if I pick a value x between a and b, here, as it is a line, I can compute c and d, and this value here is exactly cx plus d. And you can see in this picture, in this figure, that cx plus d, whatever the value of x is, will be always smaller than the logarithm of x. Always smaller for any values between a and b. Is it okay?
Yes, sir.
So, for example, so we will see now the proof of Kramer-Chernoff calculation. I assume that my random variable x1, xn are independent, so I can compute the Laplace transform of Sn. The Laplace transform of Sn is a mean of the exponential of t, the sum from 1 to n of xk. Exponential a plus b is exponential a times exponential b. So the exponential of the sum is the product of the exponential. And as my random variables are independent, the mean of the product is the product of the mean. Okay. So the logarithm on both sides. So the logarithm of the mean of the logarithm of the Laplace transform of Sn is the logarithm of the product, and the logarithm of the product is the sum of the log. Log of A times B is log of A plus log of B. The logarithm of the product is the sum of the log. Now, I can use the concavity of the logarithm function. Okay, so if I divide by n in both sides, I have 1 over n, the log of the Laplace transform, is equal to 1 over n, the sum of the log. And now, from this draw, 1 over n sum 1 over n sum from 1 to n of log of ak, for example, will be always smaller than the log of 1 over n sum of ak. I repeat myself, from the concavity of the logarithm function, if I choose any value a1, a2, an in a positive value a1, a2, an, 1 over n, the sum of log of ak, will be always smaller than log of 1 over n sum of ak. Okay? So we are done because this quantity is my LT. This quantity is my LT. Okay. So do you have questions? No questions? So in the proof of Hofding inequality, we use the convexity of the exponential function. And in the proof of the Kramer-Chernoff calculation, we use the concavity of the logarithm function. Okay. So this corollary was established by Chernoff in the special case of a binomial random variable. And later, it was improved by Hofding for any sequence of integrable and independent random variable. Okay. So the result is as follows. x1, x1 are at integrable and independent random variable. I assume that they are sharing the same mean, only the same mean. Then for any x greater than this mean, the probability that Sn is greater than n times x is always smaller than exponential minus n times L star x I have a question for you now. Do you have any idea of the proof? You have to recall what we saw yesterday. Do you have any idea how to prove this?
Sir, we have used inequality that probability Sn greater than nx is equal to probability e to the power Sn greater than equal to e to the power nx. In the previous day we have used this, and
Yes.
depending on that inequality we should work on that, and after we get L star x. And
What do you mean that we should work on that? What is the idea now?
sir, I can't I don't able to tell because I have to think on that. So I know how the proof will go, but I have to calculate it.
Okay. So we will do it together. So it's very simple if you understand well what we saw yesterday. We just have to use Markov inequalities. Markov inequality. Probability that Sn greater than nx, you can multiply on both sides by a positive quantity t, and you obtain that it is smaller than exponential minus n tx, because you have n here, the Laplace transform of my random variable Sn. But what we saw that the Laplace transform of my random variable Sn is smaller than exponential nLt, is smaller than exponential nLt. So here you are, the upper bound is exponential nLt. So if I make minus n, if I make a factorization with minus n, you have a minus LT, because the upper bound was exponential nLt. So minus n here, tx or xt is the same, and the upper bound was exponential nLt, so it's necessary to put a minus L here. And the idea was exactly the same as the one we saw in the introducing example yesterday. Now we make an optimization over all positive values of t. So by taking the supremum over all positive values of t, because t we can choose it as we want, because the left-hand side does not depend on t. We choose a value of t which maximize the function here. The function phi t, which is xt minus lt. So we can put the supremum, and this is exactly the definition of L star x, the supremum. Do you understand well this proof?
Sir, can you please repeat this? I have left from. I have got disconnected from the
Okay.
this classroom.
We start as yesterday. Probability that Sn greater than nx. Here, if t is a positive value, it is exactly the probability that exponential t Sn greater than exponential t nx. So from Markov inequality, this is smaller than exponential minus n tx times the Laplace transform of Sn. And previously, we saw that the Laplace transform of Sn is smaller than exponential nLt. The Laplace transform of Sn is smaller than exponential nLt. So if I make a factorization by minus n, you have minus n times xt, and I have to put a minus lt. So finally, you just have to make an optimization over all positive values of t, and you obtain exponential minus n L star x, where L star x is the supremum over all positive values of t of xt minus lt. You got the proof now?
Yes, sir.
Okay, good. So we will see examples now. We will see 3 examples where the Kramer-Chernoff calculation works well. Imagine you have Bernoulli random variable, a sequence of Bernoulli independent random variable. They are not sharing the same parameter p, but they have different distribution, and the distribution is a Bernoulli bpk. Okay. It means that xk takes 2 values, one with probability pk and 0 with probability 1 minus pk. So I will denote by p bar n the mean of my pk, 1 over n sum from 1 to n of pk. So for any x between 0 and 1 minus p bar n, you can't show that the probability that Sn minus its mean is greater than nx is smaller than exponential minus n phi of x, where phi of x is given here. Okay. And I have a second result, which is given by Hovding inequality. But the first result here is more sharp than the second result given here. Okay. How you obtain this function phi? You just have to compute what is L star. What is L star here? You just have to compute the L star given here. Okay, just have to compute the L star. Here I put minus the mean. It's not a problem. It's okay. You just change the function L. And as I said, the proof relies on the Kramer-Chernoff calculation, and we will now see why. What is the Laplace transform of my random variable xk? Xk takes 2 values, 0 with probability 1 minus pk and 1 with probability pk. So the Laplace transform of xk is 1 minus pk times exponential of 0, exponential of 0 is 1, plus pk exponential of 1. So you immediately have this result. So now I can compute my function LT. LT is 1 over n, the sum of the Laplace transform. LT is log of 1 over n, the sum of the Laplace transform. So LT, I make a plugging of the Laplace transform. It's log of 1 over n, 1 minus pk plus pk exponential t. So 1 over n, the sum from 1 to n of 1 is 1. 1 over n, the sum from n to 1 of pk, it is exactly p bar n. And the last term, 1 over n, the sum from 1 to n of pk times exponential t, it's p bar n times exponential t. And then, now you compute L star, and you have the result. Easy. Okay. Easy. You obtain a result. Okay, this result here. It's just compute, make a max compute L star. Very easy. Okay. A second result was established by Janson 2 years ago, only 2 years ago, in 2018, 2 years ago. Imagine that you have a sequence of independent random variable with different geometric distributions. So the probability that xk takes a value L is given by pk 1 minus pk at the power L minus 1 for all L greater or equal to 1. So this is the geometric distribution. You can compute the mean value of Sn, and now it's not p bar n, it's p hat n, which is the minimum of all values of pk. Then you have a result similar to the previous one. Probability that Sn minus the mean is greater than nx. Here you have nx, but now we will not have nx. Is smaller than this quantity. Here you don't have n. I can explain why, but it's not necessary, I think. And it's smaller than exponential minus p hat n times phi of x. And phi of x is this quantity. A natural open problem, open question. Can you improve this result? Can you prove it for the gamma distribution, for other distribution? And a more interesting result, which can be found in the Janson paper, can you establish a lower bound for this probability? And if you look at the paper of Janson, you will have a lower bound. Now, exponential distribution. I assume that my random variable x1, xn are independent, and they have exponential distribution with parameter lambda k. So the exponential distribution can be compared to the geometric distribution. It's a continuous distribution. It is a continuous counterpart of the geometric distribution, which is a discrete distribution. So the results are quite similar. Before it was p hat n, which was the minimum of all the value of pk. Here is lambda hat n, the minimum of all the values of lambda k. And the result is exactly the same. The function phi here is the previous function phi here. So exactly the same. So as before, in the paper of Janson, you have a lower bound for this probability. And a natural open question, can you prove similar concentration inequality for the gamma distribution? because the exponential distribution is a special case of the gamma distribution. Okay, so if you can do it, it will be very good. The question is, how can you improve Janson results replacing the exponential distribution by the gamma distribution? A natural question. Okay, I've finished.
Thank you, Bernard. Thank you.
Thank you.
Students, if you have any questions, please raise your hand, ask him. Students?
Sir,
Yes, sir.
I have a question. Can I ask?
Yes, Shankar. Yeah.
Sir, in Bernoulli distribution, sir, write x lies between 0 to 1 minus p n bar. Sir, why we write the upper bound 1 minus p n bar?
For the Bernoulli distribution, I don't.
Sir,
For the Bernoulli or for the geometric?
binomial.
Bernoulli distribution. Why this P(n) bar occurs? This is your question?
The range of x lies between 0 to 1 minus p n bar. Sir, why 1 minus p n bar we take?
Ah, here. Oh, the
Yes, sir,
question.
yes, sir.
Okay, I understand your question. Okay. Sn is the sum of Bernoulli random variable. So the minimum value, so it's a binomial random variable. For the minimum value of Sn is 0, and the maximum value of Sn is what?
N.
N. So the minimum value of Sn over n is 0, and the maximum value of Sn over n is 1. Okay?
Mm-hmm.
So what is the mean of Sn? The mean of Sn is npn bar. So if I divide Sn minus the mean of Sn by n, the maximum value that can take this quantity, Sn minus the mean of Sn over n, will be 1 minus Pn bar. So if x is greater than 1 minus Pn bar, this probability is 0. This is why we have to assume that x is smaller than 1 minus Pn bar.
Thank you, sir.
You're welcome. Other questions?
Sir, Kramer-Sharnoff inequality, in the statement it is written that x1, x2, xn follows any IID random variable. So
Yes.
this inequality can be proved for any distribution rather than gamma, normal distribution, chi-square distribution.
Yes. I just show you three example: Bernoulli, geometric, exponential. But you are totally right. It is also true for gamma distribution, for chi-square distribution, for any distribution with. The only difficulty is to compute L star. So in if you take a complicated distribution, it will be complicated to compute L star. But this is true for any distribution.
Okay, sir.
You're welcome.
Any other questions, students?
Sir, can you also talk about applications of concentration equalities in machine learning? Like talk about some applications.
Yes. I've written a paper with a PhD student in electronic journal of probability in electronic communication in probability last year, and you have an application. Can I can show it to you, but it's a long story. It's let's have a look to this paper. Electronic communication and probability. So I will stop to share and I will show you the paper. You can see this paper?
Yes, sir.
Okay,
Yes,
so it's electronic communication and probability last year, and it is dealing with concentration inequalities for martingales. So it's a long story, but I show you the application. This, for example, online statistical learning. On online statistical learning, you have many applications, because you have many people working on the statistical learning, deep learning, etc., etc. And if you are able to produce a concentration inequality like this one, you will prove this kind of result, and they are very interesting result. It dealing with empirical risk and average empirical risk. So the empirical risk is given by this quantity, and the average empirical risk by Rn given here. Here, L is a bounded function, my little n, bounded by 1 here. So I can use Hovding inequality, but it's not good. You can improve the Hovding inequality, and in that case, using the theory of martingales, you will obtain this upper bound. And the good thing in this upper bound is that you have the Vn term here, the variance term here. So you will improve many of the results in the literature. And for example, in this paper, we have improved a paper of Cesar Bianchi, which is and Lugosi. They are experts in this field, but our bonds are much more better than their bonds, for example. So in the way to evaluate average risk in statistical learning, in online learning, you have many applications.
Thank you, sir. I think I get an idea.
Okay. Other questions?
Sir, in this paper, it is written about the self-normalized Marty angle. Sir, I don't know about Marty angle. Can you please tell?
No, it's too long. I am an expert of martingales, but it's not easy to explain in 5 minutes the theory of martingales. It's too long. It's I can give more than 20 hours a course about martingales, and it will only be the introduction. It's a very large topic, and I cannot explain it in 5 minutes. It's impossible. Impossible. Sorry.
Okay, sir, no problem. Thank you, sir.
You're welcome.
Any other questions, students? Seems to be very quiet. So, okay. So, students, if there is no other questions, please thank Professor Bernard Bercu for these two wonderful lectures on concentration inequalities. Please unmute your button and unmute your mic. Okay, and give him hands.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you very much.
Thank you, sir.
And
Thank
you
you,
can
sir.
Thank you, sir.